Okay, cool. Yeah. So hi again. So today we'll be discussing the Codeforces Educational Round 141. And yeah, hopefully the contest was good for you guys. We'll be discussing the first five problems. So let's start with problem A. Yeah. All right. So here there are like two strings which will be given to you, and every string is essentially either every character of every string is either an R or a B. R denotes a red block and B denotes a blue block. Essentially, what you can do is you can take out the last character of the first string and append it to the end of the second string. Okay. And what you want to do is you want to make sure that after you have performed all the operations that you want to perform, uh, there are no two adjacent cells in any of the strings such that both the cells have the same color, right? So yeah, this is the problem. I think it's pretty easy. All you have to do is you have to make this one easy observation here that like no matter what you do, let's say you do some X operations from the first string to the second string, right? And then you do some Y operation from the second string to the first string, right? And let's say x is greater than y, then essentially all you did was you did x minus y operations from the first string to the second string, right? So all it means is that no matter how you do operations, you are essentially going to move some suffix of the first string to the second string, or you can move some suffix of the second string to the first string. Okay, so once what you can do here is you can iterate on all the suffixes and you can check whether your string is good or not, right? So yeah, that's the solution. Pretty easy if we just have a look at the code. So the code is pretty simple. All you have to do is you can iterate on all the prefixes. For example, here I'm iterating how many characters am I moving from the first string to the second string. And then I'm just checking whether both the strings are good or not after this operation. So you'll have to do this the other way around as well. That is, you'll have to move from S2 to S1. So I just made a custom function called solve, and then I checked it for S1, S2, and for S2, S1. So yeah, this is the solution to problem A. I mean, obviously there might be some easier solution, but this is what struck my mind when I read the problem. So yeah, we won't be spending a lot of time on this problem. Let's move on to the more interesting ones now. Okay, so let's move to problem B. So I'm audible, right? Can anybody confirm? Yeah, okay, okay. Cool. So yeah, problem B says that we are given n ranges. Okay, so a range is nothing but a pair of integers L comma R. And what we need to do is we need to tell we are given an integer k and we need to tell whether or not it will be possible, to remove some segments so that the number k becomes ideal. And the definition of a point x being ideal is that fx should be greater than fy for all y. And the definition of f is that f of x is nothing but the number of ranges in which the number x occurs, right? So if there is a range from L to R, then we'll say that all the numbers from L to R have a 1 incremented to their F value. Okay. Now all you need to check is you need to check whether or not it's possible to remove some or none of the ranges such that f of k becomes greater than f of x for all x not equal to k. Okay. Yeah. So the main observation here is that we need to see what happens when it is not possible to make f of k when it is not possible to make the point k ideal. Okay, so what exactly happens when we are not able to make k ideal? So what happens is that like it is not possible to have f of k greater than f of x for all x. Okay, so this is the condition that we want to avoid, and we want to tell whether or not it's possible to avoid this condition. So one main observation here is that in every range where there is a k, so like, yeah, so the main observation here is that we don't need to check for all the x's. We only need to check for x is equal to k plus 1 and x is equal to k minus 1. Okay. Why? The reason here is that let's say there is some y such that f of x f of k is equal to f of y in this case, and let's say that y is greater than k. then it is always the case that f of k plus 1 will always be equal to f of k is equal to f of y. The reason being that if there is a range in which there is k and there is also a range in which there is y, then there is obviously k plus 1 as well in that range, right? And similar is the case with k minus 1. Okay. So yeah, here is the claim that we only need to check x equal to k plus 1 and x equal to k minus 1. And yeah, if there is a range which contains x equal to k and does not contain x equal to k plus 1, then we are good. Similarly, if there is a range which contains x equal to k minus 1, which does not contain x equal to k minus 1 but contains x equal to k, then we are good. But if neither of these cases hold, then we can say that x equal to k plus 1 will always be present when k is present. So f of k can never be greater than f of k plus 1, right? So yeah, this is the main observation of this problem. So the code again is pretty simple here. What we do is we check all the ranges which contain k, okay? And we'll check whether or not that range also contains k plus 1. So if that range ends at k, then that means it does not contain k plus 1. Similarly, if that range starts at k, then that means it does not contain k minus 1. So if both of these conditions hold, that is, we found a range which contains k but does not contain k plus 1, and we also found a range which contains k but does not contain k minus 1, then we are good. So in that case and only that case, the answer is going to be yes. So I hope the solution is clear. If you have any doubts, you can ask, and if that's not the case, then we'll quickly move on to problem C. Okay, I guess there are no doubts. That's good. Yeah, so this one was a particularly interesting problem according to me. Like, falls into the category of my favorite problems. You only need a little bit of observation to solve this, and it's also not very easy. So it makes up for a very good div 2C problem. Yeah. So I hope all of you have read the problem statement. I will just simplify it for you guys. So what happens is that there are a few iterations in which the people are going to taste the coffee or the tea, whatever it is. In the first iteration, the ith person will taste the ith coffee. In the second iteration, the first person finishes tasting, and the ith person will now taste the I minus 1th coffee. And in the second iteration, the first two people will not taste anything, and the ith person will taste the I minus 2th coffee. Okay. So yeah, essentially what happens is that after the ith iteration, the ith person finishes his tasting, and the ith coffee from the right, the ith tea from the right becomes irrelevant. Okay, so this is what happens after every iteration. And finally, what we need to tell is we need to tell for every person how much coffee or how much tea is he going to drink. The caveat is that for every type of tea, so for the ith type of tea, we have exactly AI milliliters of that present. And also the ith type of person can, in one iteration, drink at max BI amount of coffee. Okay. So yeah, we need to tell for every person how much tea will he drink in this entire process. So yeah, let's start with the solution. So in the solution, I'll just like to start with this one quick observation. So what you do is you don't think in terms of people, think in terms of every tea. Okay, so think in terms of every tea. So for the ith tea, let's think about how much of it will the jth person drink, right? We can think of it like this, right? So let's focus on the ith tea, right? So we have all these teas and we have all these people. Let's say this is I. So we have AI amount of this tea present. Now in the first iteration, this tea is going to be drunk by the ith person, right? And this person has a capacity of BI. Similarly, in the second iteration, this tea is going to be drunk by this person BI plus 1, right? And so on and so forth. But here is the catch. In the first iteration, so let's make two cases. So in the first iteration, two things can happen. Either the first person can completely finish either the ith person can completely finish the ith t, or he will finish his own capacity bi, and ai will get decreased by bi. Okay. So the first case is that ai becomes zero, and the second case is that ai becomes ai minus bi. Okay. Now, if AI becomes zero, then that means that the IHT will now not contribute to any other person and our work is done. We can just say that the IHT contributes AI to the ith person and then it contributes nothing to anyone else. Right? So if this is the case, then we are done. But if this is not the case, then what happens is that in the third iteration, now the I plus one, sorry, in the second iteration, now the I plus one person will come and he will try to drink the ith amount of tea. And we know that we have ai minus bi amount of t, right? Then again, there are two cases. So the first case is that the ith person will finish this entire t. So we have ai minus bi, and the ith person will finish this entire t. So now it becomes zero. And the second case is that the ith person, sorry, the I plus one person, it just takes the maximum capacity that he has, which is nothing but bi plus one. So from ai minus bi, we go down to ai minus bi minus bi plus 1. And now I think you guys can clearly see what's going on here. So the ith type of T basically does something like this. So it will completely satisfy some of the people. Okay. It will completely satisfy some contiguous amount of people, and whatever is left will be given to this person, right? So yeah, this is the main catch of this problem. So we just need to find out this range of people that this IHT will completely satisfy, and the leftover we will give to this person. And how can we do this? We can do this with a simple binary search. So we can use a simple lower bound on the prefix sums of B to find out the first j such that, so you need to find out the first j such that bi plus up till bj, this value exceeds, so this value is strictly greater than ai. So if you find out such a j, then this j is like this. And so all the people from I to j minus 1 will get their required quantity of t, which is nothing but bj, sorry, which is nothing but bi. And the jth person will get ai minus the sum of all these bi values. Right. So this is the main outline of the algorithm that we'll be using. But now there is one more problem. There is a problem to implement this effectively. So even if we find out j fast enough using binary search, we need a method to quickly increment all these values. So we need to increment answer. So we need to increment answer of I. So let's say we need to increment answer of k plus equal to b of k for all k in this range from I to j minus 1. And if we naively do this, then obviously this is going to TL. So there is a very well-known technique which is used to solve problems like this, and that is known as the difference array technique. Okay, so I hope you guys are familiar with what difference array is. If you guys are not familiar with difference arrays, then I think you should first look up what a difference array is and what it does. So essentially, instead of doing this entire costly process, we can maintain a difference array and we can do a plus one at the position j, and sorry, we can do a plus one at the position I, and we can do a minus one at the position j. And essentially, finally, we can take the prefix sum. So we can take the prefix sum and that will give us the final value of that array, of the array at that point, right? So in this way, we can do this operation in constant amount of time. So in total, our algorithm works in O of n log n time, right? So the bottleneck is this binary search that we use to find out the value of j. Cool, right? So yeah, this is the solution. Let's just quickly have a look at the code. Yeah, here is the code. So I create two arrays. First is the difference array, and the second is that extra array. So that extra is nothing but the extra amount that I'm adding to the jth person. So I'm keeping that in a separate array. So for every I just using upper bound find out the value of j. Okay, and then I say diff of j minus minus and diff of I plus plus. And then also the remaining amount of the ith t will go to the jth person. So extra of j will be ai minus the sum from I minus 1 to j, sum from I to j minus 1, right? And so now I take the prefix sum of the difference array, and this is how we use difference arrays. So the final amount of tea that the ith person is going to drink is going to be extra of I plus bi multiplied by difference of I, right? Cool. So yeah, this is the solution to problem C. I hope it is clear to everyone. If you guys have any doubts, again, you are free to ask. Any doubts here? Yeah, hi. Mhm. Yeah, exactly. Yeah, extra. Yeah, yeah, exactly. Yeah, yeah, exactly. All right. So any other doubts here? Cool. So yeah, let's move on to problem D now. So this is like problem D, I would say is not a very good problem according to me. It's like it's not that hard. It's like really easy, I would say, for its position. It's just that they tried to make it hard by introducing these undirected graphs and stuff like that. But at the end of the day, it boils down to a very simple combinatorics problem. So yeah, that's my take here. Let's start with the solution. So essentially what happens is that we are given like some n by 3 groups of vertices, and every group has exactly 3 vertices, and there is an edge between each pair of vertices in a group. Like so there are 3 edges in every group. In total there are like n edges since there are n vertices. Now what we need to do is we need to color these vertices into either red or blue colors, and like exactly half of the vertices should be colored red and the other half should be colored blue. Okay. Now the catch here is that we need to do it in such a way so that so that the weight of all the chosen edges is maximum. And the definition of a chosen edge is that both the endpoints of that edge belong to different colors, right? So with that definition, we need to make sure that in our coloring, the weight of the sum of weights of all the chosen edges is as much as possible. We are provided with the weights of all the edges in the input, so that's not a problem. Okay. Now, our job is not to find one such coloring. Our job is essentially to find the number of such colorings such that the weight of the sum of all the chosen edges is as much as possible. And a chosen edge is nothing but an edge which has two different colored endpoints, with the constraints that the number of blue and red colored points should be exactly n by 2. Right? Hope the problem statement is clear. So yeah, let's have a look at the solution, how we solve this. So we have some n by 3 groups which look like this. So we have some triangles. Yeah, so do not think about it as graphs. Let's say that we have exactly n by 3 triangles, and you are also given with the length of each side of each triangle. Okay, so in this input, these wi's are nothing but the length of a side of a triangle. So yeah, you know the lengths of all the sides of a triangle. And what you need to do is you need to maximize the, yes, so you need to choose, you need to color some vertices as red, some vertices as blue, same old, and you know what the definition of a chosen vertex is. Now the question is, how do you maximize the sum of the chosen edges? Obviously, to find out the number of such colorings, you first have to figure out some kind of criteria which will maximize your sum of edges, right? And so let's focus on that criteria for now. Okay. So one important observation that we can do here is that, so from each component, so from each triangle, we can take either 0 or 2 edges. Okay. Now, why is this true? This is true because in a triangle there are like three nodes, right? So there are three vertices. So either all the three will have the same color, or one of the vertices will be colored blue, two will be red, or one of the vertices will be colored red and two will be colored blue. So if all the vertices are the same color, then essentially there is no chosen edge, so we are taking zero edges. But let's say one of the vertices is colored blue and the other two are colored red, then it is clear that we'll be taking these two edges. Similarly, you can just figure out all the cases and you can confidently say that we are going to either take zero edges or we are going to take two edges. Uh, but our goal was to maximize the sum of weights, right? So it doesn't make any sense to take zero edges, right? Since we can always take two edges, why take zero edges? Hopefully this makes sense. So we will take two edges from every triangle. But now comes the question, which two edges should we take? Now, obviously, if you want the maximum sum, then you will take this two edges such that their sum is maximum. Take two edges such that sum is maximum in each triangle, right? So yeah, this is a very obvious strategy that you can use to maximize the sum of weights. But a question arises whether it is actually possible to take all these two edges from every triangle and also making sure that we take exactly n by 2 blue nodes and exactly n by 2 red nodes. Is it even possible? It turns out it is actually possible. So the reason being that in every triangle, you can clearly see that we are either taking one blue, two red, or we are taking two blue, one red, right? So let's say that this is a type 1 triangle and this is a type 2 triangle. And we know that we are given n by 3 groups and n is divisible by 6. So that means the number of groups that we have is even. So number of triangles that we have is even. So all we can have is we can have n by 6 triangles of type 1 and n by 6 triangles of type 2. And we can clearly see that the sum of the number of red and blue nodes uh, in a triangle of type T1 and in a triangle of type T2 is exactly equal to 0, like the sum of their differences. So there are exactly three blue nodes in T1 plus T2, and there are exactly three red nodes in T1 plus T2. So if the number of triangles of type T1 is equal to the number of triangles of type T2, then obviously there will be n by 2 red nodes and n by 2 blue nodes. So all we need to do is so just choose some n by 6 triangles from the given n by 3 triangles, color them blue, and just color not color them blue, make them type 1 type of triangles, and you choose the other n by 6 triangles from the remaining n by 3 triangles and you color them red. So you color them RBB, making them of type 2. In this way, we can make sure that the number of type 1 triangles is equal to the number of type 2 triangles. And so the number of red nodes and the number of blue nodes is equal to n by 2. Hopefully this makes sense. But here's the catch that we can't just say that our answer is equal to n over 3, c n over 6. It is quite tempting to think that the answer is going to be this because all we need to do is we need to choose. Yeah. So all we need to do is we need to choose whether a triangle is going to be T1 or T2. But it turns out that that is not the case. So obviously you need to choose this. So this will be a term in your answer, but you also have to multiply it with something else. Now, what is that something else? Okay. So here we are assuming that in a triangle, now let's come to a triangle. We have looked at the distribution of triangles. Now let's look at one triangle and see the number of ways we can color it. So let's say we are trying to color it as a type 1 triangle. So we want it to be BRR type of a triangle. Okay. So our goal is to color it in such a way that color it in such a way, let's say this is W1, this is W2, this is W3. Our goal is to color it in such a way that W1 plus W2 is as is maximum possible, right? So out of these three edge weights, you take the two maximum edge weights and you color that corresponding vertex as blue and you color the remaining vertices as red. So let's say these values are 5, 6, and 7. Okay. So if all these three values are distinct, then we can say that there is exactly one way to color these, right? And that is to color this one as blue, this one will be blue, and these two will be red. Okay. Reason being that this 6 and 7 is the only combination of edges that we want. And if we know that this is the combination of edges that we want, then there is exactly one way to color it. Okay. So yeah, but let's say that this is not the case, and let's say that all these edge weights are 5. So if all these edge weights are 5, then we are free to choose the vertex that we want to be blue. No matter which vertex we make blue, the other two will become red, but the sum of the chosen edges will always be equal to 5 plus 5, which is 10. So in this case, there are like three ways. Okay. So if in a triangle all the vertices are of the same length, then there are three ways to color it. If all the vertices are of the distinct length, then there is exactly one way to color it. Now let's see if there are two vertices who are equal and one vertex which is not equal. So let's say we have 5, 5, and 10. So in this arrangement, you can clearly see that there are two ways to color it. Okay. So you can either take these two edges. So if you're taking these two edges, then this will be blue and these two will be red. Okay. But it is also possible that you take these two edges. If you take these two edges, then this vertex will become blue and these two will become red. So there are two ways to color it. Okay. So the third case is that instead of by having 5, 5, 10, you have something like 5, 5, 2. Now, in this case, again, you can see that there is exactly one way because there are no two ways to choose edges. You are sure that you will choose exactly these two edges. So there is one way. Okay. So essentially, there are four cases. So the first case is that when all the edge weights are distinct, then there is exactly one way. The second case is that all the edge weights are same, then there are three ways. The third case is that two of the edge weights are distinct, and the third edge weight is greater than that value. So in this case, there are two ways. And the fourth case is that two of the edge weights are same, and the third edge weight is smaller than that value, in which case there is exactly one way. So we will count how many triangles we have of each of these four types. Essentially, there are three types, the ones which have one way, the ones which have two ways, and the ones which have three ways. So let's say there are k such triangles. So let's say there are k3 such triangles, there are k2 such triangles, and k1 such triangles. So we will just add like 2 raised to the power k2 into 3 raised to the power k3 to our answer. Because for every triangle of type K2, we have two choices. Similarly, for every triangle of type K3, we have three choices. So our answer is going to be this value multiplied by n by 3, c n by 6. Okay, so the code again is pretty simple. All you have to do is just figure out how many triangles you have of the three types. So if all the edges are the same, then it's a type 3 triangle. If any two are the same and it is less than the third, then it's a type 2 triangle. Otherwise, it's a type 1 triangle. So your answer is going to be 2 raised to the power t2 into 3 raised to the power t3 into n over 3 c n over 6, right? So yeah, this completes the solution to problem B. So is there any doubt in this problem? So you didn't realize that triangle with two same sides has two cases. Yeah. So even I was missing that out when I was trying it during the contest. So yeah, that's kind of a tricky case here. Cool. Cool. So now let's talk about problem E. This is the last problem that we'll be discussing. I again really liked this problem, even though the implementation got a bit messy, but I think that was my fault. So yeah, this problem is quite nice. All right, just a moment. All right, cool. So let's start with problem E now. So in this problem, again, the problem statement is quite big. So let me simplify it for you guys. So essentially, what this problem is saying is that you have an array, and this array denotes the health points of the n monsters that you have. And you can do an operation and you can decrease the health of any monster by exactly one. And a monster dies if its health becomes non-positive. So if its health becomes zero, it dies. But here's the catch that you have another type of operation which is called the explosion operation. So what the explosion operation does is that you choose an index for this explosion operation. So an explosion is defined by two values, an index and a number x. So what happens is first you choose these two numbers I and x. And if hi is greater than x, then what happens is that the ith monster, like it stays alive, but its health is decreased by x, and then nothing else happens. But if that's not the case, then what happens is that the ith monster dies, okay, and it creates two explosions of hi minus one damage in the neighboring cells of I. Okay, so like now we have from one explosion of type I comma x, we have two explosions of type I minus one comma hi minus one and I plus one comma hi minus one. Similarly, these explosions can cause other explosions, so on and so forth. Okay. Now, our goal is to do some operations of the first type, that is decreasing the health of some people by one. And after that, only do the explosion exactly once so that in our explosion, everyone dies. Okay, that's what we want. Yeah. So you can read the problem here. So our goal is to kill the remaining monsters with that chaining explosion, right? So what we need to do is we need to first do some operations of type 1 and then finally we'll do an explosion such that all the monsters then die after that explosion. Cool. Now our job is to find the minimum number of operations of type 1 that we need to perform. Uh, Sorry, not the minimum number of operations of type 1, the minimum number of operations of type 1 plus the value x that will be chosen in the explosion that we perform. Okay, so we need to minimize this sum. So if you read the problem statement, it will become more clear why it is the sum. It's just an operation of type 1 costs 1 MP and an explosion of value x costs x MP. Okay, so that's it. So here's the catch of this problem. So the catch in this problem is that we look at our end goal. So our end goal is that we'll choose some index I. Okay, so let's say this is the index I that we are choosing, and we'll perform the operation on I, and we expect every monster to die after this operation. Okay, so when will every monster die? So after the ith explosion, obviously we will have two explosions of I minus 1 and I minus 2. And we need to make sure that this I minus 1th person dies. We know that the power of this explosion is going to be hi minus 1. So this is hi. So this explosion, the power of this explosion is going to be hi minus 1. And so this value, so the health of this monster, yeah, so the health of this monster, hi minus 1, should obviously be less than or equal to hi minus 1, right? Because this monster is time. Similarly, the health of the I minus 2th monster, this should be less than equal to health of the I minus 1th monster minus 1. Okay? Or it can be 0. So if it is 0, then the monster is already dead. So it should be either 0 or it should be less than or equal to this. So what I'm trying to say here is that if you do an explosion on the ith index, then your array should look something like this. So you have some decreasing values and then you get zeros. Similarly, you get some zeros. Okay. So I hope this is clear why the array should look like this. Okay. So all the other elements should be decreasing towards the left. It should be decreasing towards the right. And as soon as one element reaches zero, all the elements should be zero. Okay. So this is how your array should look like if you want to make sure that the explosion at the ith index causes every monster to die. And as far as the power of the explosion is concerned, it is obviously going to be h of I, because we only need to make sure that the power is as good as it kills the ith monster. So it's pointless to have the power. So it's pointless to have the value of x greater than h of I. So x is fixed to be h of I, right? So yeah, this is our job. Cool. So how do we solve this? So what we can do is we can solve this using dynamic programming, DP. Now, obviously, what I'll do is I'll find this answer for every index, but I will find the answer for the left part of the array and the right part of the array separately. So both the answers are being found in the exact same manner. So I'll just focus on the left part. So I'll try to find out the minimum number of operations that we need to do so that the left part looks like this and the right part looking like this will be handled in the exactly same manner. So I'll not be describing that. Okay. So let's just focus on making the left part decreasing. So this part should be strictly decreasing. Just to make sure this part is strictly decreasing, and as soon as it hits zero, every number is zero. Okay, so this is our goal. So what we can do is we can have a DP. So DPI denotes the minimum number of operations for the ith index to have the left part good, right? So what I want is I want the left part to be good and I want the right part to be good. So right now I'm only focusing on the left part. The right part would be symmetrical, so I'm not focusing on that. So we have a DP where DP of I denotes the minimum number of operations that we need to do so that the ith, so that to the left of I, every number is either decreasing or is zero. Okay, so this is what my DP denotes. So let's see how we can compute these DP values. Okay, so we are on the ith index and we want DP of I. Okay, so let's see what happens. Let's say that the I minus 1th number, h of I minus 1, is somewhere here. So let's say that h of I minus 1 is in fact greater than h of I minus 1. So as I've already stated, the condition that the explosion kills him is that h of I minus 1 is less than or equal to h of I minus 1. But let's say that's not the case. So if that's not the case, then we'll have to decrease. So then we'll have to decrease hi minus 1 to h of I minus 1, right? But let's say that was not the case. So let's say h of I minus 1 is less than or equal to h of I minus 1. If this is the case, the interesting thing that's happening here is that we can forget about I, we can only focus on I minus 1. We can make the prefix I minus 1 good and the prefix I will automatically become good. So we can say that dp of I is going to be dp of I minus 1, right? So if this is the case, then we are done. But if this is not the case, let's focus on the first case again, right? So in the first case, we saw that if h of I minus 1 was greater than h of I minus 1, then we will just convert h of I minus 1 to h of I minus 1. And the number of operations that it will take is nothing h of I minus 1 minus h of I minus 1. Okay, these many operations it's going to take. So now let's focus on I minus 2. Again, there are just the same two cases. So if h of I minus 2 is now greater than h of I minus 1 minus 1, then we'll have to convert h of I minus 2 to h of I minus 1 minus 1. Okay, so you convert. But if you find out that h of I minus 2 is less than or equal to h of I minus 1 minus 1, then you can just end your search here and you can say that dp of I is going to be dp of I minus 2 plus you are converting the I, remember that you are converting the I minus 1th number, right? So let's say this cost is C. So dp of I is equal to dp of I minus 2 plus C. So in general, if we don't focus on I minus 1, I minus 2, and so forth, so on and so forth, if we focus on some value j, now remember that as soon as we find a j such that h of I minus j is greater than, oh, just a moment. So this shouldn't be h of I minus 1, right? This should be h of I minus 1 minus 1. Because we are converting, first of all, we are converting h of I minus 1 to h of I minus 1. And so now when we look at I minus 2, we have to make sure that it is less than or equal to h of I minus 1 minus 1. Okay. So in general, what happens is that if we find out a j such that if we find out a j such that h of I minus j, or let's say h of j So if h of j is less than or equal to h of I minus I minus j, right? If this happens, then we can say that dp of I is equal to dp of j plus cost of converting all the elements from I plus 1 to j minus 1. So calculating this cost is easy. Like you can use some prefix sums to calculate this cost. Okay. Let's see how we can do this. So yeah, this is not very hard. So all you need to do is for all k in I plus 1 to j minus 1, essentially what you are doing is you are converting h of k to h of I minus I minus k. Okay. So the cost that it is going to take is nothing but k goes from I plus 1 to j minus 1 h of I, sorry, h of k minus h of I minus I plus k. Something like this. Okay. Yeah. So yeah, essentially what you are doing is you have h of k and you are converting it to h of I minus I minus k. Sorry, this would be plus I minus k. Yeah. So this is what your cost is going to look like. So this is pretty easy. What you can do is you can store some prefix sums of hi minus I. So then you can use those prefix sums to calculate this cost in O(n) time. I hope this is clear how you can calculate this cost in O(n) time. So yeah, the main challenge is to find this j. Okay, so you need to find the first j, which is smaller than I, such that h of j is smaller than equal to h of I minus j. So let's focus on finding this j. So h of j is smaller than equal to h of I minus I minus j. So if we expand it out, we get something like this. H of j minus j is smaller than equal to h of I minus I. And we need the rightmost j smaller than I, which satisfies this condition. Now, there is a very standard trick using which we can find out this j pretty quickly. I think we also discussed this in the last contest discussion that we had. So all you need to do is you need to have a stack. So you can use a monotonic stack to find out this for every I. Okay. So you know that using a stack you can find the next smaller element, right? So all you need to do is you build up another array. Let's say b of I is equal to hi minus I, and then this index j is nothing but the next smaller element of b of I to the left. Okay, and you can very easily find it out using a stack. So then the algorithm becomes pretty simple. You find out this j using a stack, and you say that dp of I is equal to dp of j plus the cost to convert the numbers from j plus 1 to I minus 1, and that cost is nothing but summation I plus 1 to j minus 1 hk minus k minus hi minus I. So this hi minus I is a constant, so this can be taken out of the summation. All you are left with is hk minus k. And this summation is pretty easy to calculate using prefix sums. So yeah, in total, in linear time, we have found out all these dp values. So yeah, so this way you can find out the dp values for the left half, and in a completely symmetric way, you can solve for the right half. And then you can add those dp values. So the answer is going to be for every I, the minimum cost is going to be dp left of I plus dp right of I plus h of I. H of I is going to be the cost of your explosion. Okay. So this is how you solve this problem. I have not taken into consideration one case here, which is that let's say you have, so let's say you have a number here, but you find out the next smaller element, which is here. But in this next smaller element, when you keep decreasing, let's say instead of 5, it has 3. Yeah. So let's say here you find out the next smaller element of 3. So you will have to convert this number to 2. You will have to convert this number to 1. You will have to convert this number to 0. But you can't convert this number to minus 1, right? So you will have to convert this number to 0 only. And all the other numbers also to 0. Okay, so in that case, the transitions will be a bit different. You won't be using dpj values. So if this is j, you know that you need to convert all of this to 0. So all you need to do is you need to just add all the health values. So you need the h1 plus h2 up till hj, which can be again easily computed using prefix sums. And then the cost of converting everything in this region, which is again similarly calculated using prefix sums. Okay. So yeah, this is like a corner case, you can say, or just a slight implementation detail. It's not that important. You can figure it out yourself. But yeah, so yeah, this is the solution. Let's just have a quick look at the code. So the code again is not that clean here. So I'm calculating all these arrays. So bi is equal to ai minus I, ci is equal to ai plus I. So if you try to solve it for the right half, you will notice that instead of ai minus I, you are using ai plus I. So again, that's just an implementation detail. So you'll use a stack and you'll find out the next smaller element for every b, and then you will calculate these dpl values. So there will be two cases. The first case is here that you are getting a zero. By getting a zero, I mean you are getting into a situation like this. Okay. And if you don't get into a situation like this, then the transition is pretty easy. It's going to be dp of j plus the cost of converting elements from j plus 1 to I minus 1, which can be easily calculated. And you symmetrically solve it for the right half. And once you have these dp values, then the answer is going to be the minimum of dpl of I plus dpr of I plus a of I. Okay. A of I is nothing but health of I, right? So yeah, now I'll take doubts. I think there might be some doubts in this solution. So yeah, fire away if you have any doubts. All right, you thought of an approach, but you weren't able to implement. No problem. So yeah, does anybody else have any doubts here? Hopefully it's clear to everyone. Cool. So if this is clear to everyone, I think we can end today's discussion here. Let me just stop the recording.